to kind of harken back to your geometry days, you guys probably learned about, oops, need some color here, about congruent triangles. Okay, side, 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 angle, side, angle, side, angle, angle, angle. Well, angle, angle, angle shows proportionality, but not congruence because you don't know any side lengths. And then angle, angle, side. You always have to have at least one side length. Yes, but there is one other case that we have to be careful about, because I don't know if you guys remember, you can't use this one because if you reverse the order, it spells a bad word. Okay, so this one is a bad thing. This is the ambiguous case. Okay, and so you have to be really careful with this one. You don't want to assume that there's only one solution in that case, because there's actually no way to prove congruence with those without that situation there. So that's why you couldn't use that in geometry to prove congruence, because it turns out you don't know that they're congruent when you are given that information. There are some others, okay, but they're specialized, like hypotenuse leg, which is just right triangles, and so you already know an angle. Okay, so there's other that are out there, but these are the ones that we're going to focus on right now. To start out with, they are kind of broken into two groups for us. These are the two groups. Notice that in this group you have more sides, and in this group you have more angles. Okay, and when we talk about the law of cosines and the law of sines, generally when you have more sides, you use the law of cosines. And when you have more angles, you use the law of sines. And then we have this special case here, which we'll talk about later. This is called the ambiguous case. We should probably talk about, though, what are the law of sines and cosines? And you guys are probably going to recognize the formulas for them. So for the law of sines, it says that basically in English, what it says is that the sine of an angle is proportional to the length of the side opposite that angle. So if I go, if I take the length of a side, and then I go to the angle on the opposite side of the triangle, we would label that capital A. And I know that this ratio, the length of the side of an angle, or the length of a side, divided by the sine of the angle opposite that side. So if I was to draw a triangle, all of the formulas that I am doing here rely on a triangle being labeled this way. Okay, doesn't have to be a right triangle. Well, this ratio has to be true not just for side A, but it's true for side B, and it's true for side C. So the ratio, whatever ratio you get when you divide, uh-oh, did my pen die? What just happened? Ah! Not quite sure what happened there. So that should be sine of C. So sorry about the big mess there, big scribble. So that's the law of sines. The ratio between the length of a side and the opposing sine of the angle, or the sine of the opposing angle, is a constant in any triangle. So I'm going to delete that because it's a mess. Okay, so that was the law of sines. The law of cosines is a completely different relationship. And in fact, it is actually the general case of the Pythagorean theorem. The Pythagorean theorem only works with right triangles, but the law of cosines says that if I was to take a right triangle and lean the length of this backwards a little bit, so if I take that side and lean it backwards, now the angle is bigger. What happened if this side is the same and this side is the same? So I didn't change the length of this, and I didn't change the length of this. It's congruent to itself. What happened to this side? It increased. Okay, so as you increase this angle right here, the length of this side increases. And it turns out that if you start with the Pythagorean theorem, you can actually make an adjustment to the length of that side using the angle that you have right here. And that's what the law of cosines is it's basically the general case of the Pythagorean theorem. It works for every triangle, not just right ones. And it says that the length of this long side C, the hypotenuse, squared, is a squared plus b squared with an adjustment for the angle that we, the angle that we just opened up there, which would be angle C, because it's opposite side C. But I can write this in any order. So I can say b squared is a squared plus c squared minus 2ac cosine of b. Notice that that's a b, and that's a b, that's a c, and that's a c. And what would the last one be? 2bc. So notice that these match these. Yes. Okay. All right. So then those are the three ways of writing the law of cosines. Okay. And it's just a way, since it's not a right triangle anymore, the orientation of the angles and sides no longer matters. Okay. And so same thing with the law of sines. It's not a right triangle, so that's why all the ratios are equal to each other. Orientation doesn't matter of the triangle. So now that I've got those formulas out of the way, we need to try to solve a problem. And so the big thing about solving problems with these is knowing which formula to use. So let me clear that if it's okay. And let's try solving a problem. So we're going to just take a problem. I must be accidentally clicking a button. Let's suppose that we are flying over a highway and we're able to determine the angle that we have to look down. So let me draw a picture. Here's our plane. Let me draw this highly realistic looking plane right there. Okay. So we've got this plane. It's flying along in a straight line over a highway. So here's like the horizon line of the plane. Here's the highway along the bottom. And when the pilot looks down at an angle of 48 degrees, and if we look down at 48 degrees, then we see a point down here on the ground at one end of the highway. Okay. And then when we look the other direction, and this behind us basically, if we look behind us at an angle of 18 degrees, then we see the other end of the highway, we'll call point B. Okay. We know that the highway, looking at Google Maps or something, we know that this highway is exactly 5 miles long. Okay, from one point to one point. And I'm not saying the highway ends there. It's just like there's some, like maybe it turns sharply, and so we can see exactly where those are. But that section of the highway we know is exactly 5 miles long. The question then is, how far away are we from each of the points, and also how high is the plane off the ground? And we can use either law of sines or cosines to solve this problem, but we need to decide which one applies. Based on the drawing, is there anything else that we know? So this has to be 114 because 180 minus 48 minus 18, and it's 114, you said? Okay, other people can check that to double check. If the plane is flying level, what's true about this line and this line? They're parallel. And if you guys remember, there's a property from geometry that says alternate interior angles have to be equal. Okay, so not only can you get this angle up here, you can actually get these two as well. So using this relationship, this would have to be, oh, darn it. This would have to be 48 degrees, and this would have to be 18 degrees. And so now I have an angle, I have a side, and I have an angle. So which of the four cases that we talked about at the beginning do we have? Angle, side, angle, which means we use which law? Law of sines. Okay, so if you have more angles than sides, use the law of sines, with the exception of the ambiguous case, which we'll talk about tomorrow. We're going to use the law of sines then, and in order to do this, I need to use, it turns out that the reason this works is because of what you guys noticed. That angle has to be 114 degrees, which means I have an angle opposite a side. And so when I go to write, if this is A and this is B, I'll call this C then. And if I level this side A, this side B, this would be side C, because I got to be consistent. So angles opposite sides. So that means that angle A and side A are related. So side A I don't know, but this would be the sine of 48 degrees. That has to equal B over the sine of 18, because that's the angle opposite that. And that has to equal C over the sine of 114. So now what I want to do though is I'm not going to solve this whole thing at once. What I'll do is decide what I need to know. So for example, if I wanted to know the distance from here to here, then I could find B. Now it turns out that what I really want to know is the altitude. So the question I'm going to ask is, find the altitude of the plane. Yes. Yes, so I'm asking how tall is that right there? But the problem is, I don't know how long this edge is, and I don't know how long this edge is. But if I can find one of these edges, then I have a right triangle with a side length, and I can find the altitude. So what we're going to do then is choose either A or B. It doesn't matter. This is probably the easier one because they're next to each other. And I'm just going to take that piece of that formula. So you take two pieces of the law of sines, you set them equal to each other, and then you solve for whatever variables remaining. And so right now we have B over sine of 18 equals 5 over sine of 114. And so I'm going to go to the next slide here. So the equation is B over sine of, what was it again, 18? Equals 5 over sine of 114. And then we're going to solve that equation. So 5 sine of 18 equals B sine of 114. And I want B by itself, so I think I'll just divide by the sine of 114. which means B is equal to whatever this mess is. And then I can plug that into my calculator and actually calculate that out. What mode is your calculator in, degrees or radians? Yes, you have to always pay attention to the units. Units are so important when you're solving problems. Okay, so then in our triangle, we had a triangle that looked like this. Here's angle B, here's side B. So this is the shorter side, so that's right. 1.6913. What? Miles. Okay. So then I know that length now, which means that if I go, I can find this length now because this is a right triangle right here. This altitude, I'll call it H or something. We now have a right triangle, and I know this angle right here. What was this angle? 48? So now I can use just a regular sine function. And why did I choose sine and not cosine? Okay, I have the opposite over the hypotenuse. So then the sine of 48 degrees has to equal opposite over hypotenuse. And then solve that for h by multiplying that over. And so you're going to have h is 1.6913 sine of 48. And so our answer is going to be approximate because we've already rounded. Okay, and that's in miles. And you could change that to feet if you wanted to, like if you wanted an equivalent, because usually altitude is measured in feet. But if you took that, multiplied it by 5280, so the height in feet would be about 6,636 feet. And what were the significant digits in the original problem? So then if we were to use significant digits, yes, so it'd be approximately 7,000 feet. So it really depends on the accuracy the problem is asked for. If they say that they want more accuracy, answer their question, okay? But if they don't, then you need to make sure you're using significant digits because you don't want to lie to people that you had more information. 5 miles is a rough approximation. So your answer needs to be a rough approximation. You can't be more precise than that. So make sure that if the problem says to use sig figs, make sure you do. However, as you guys have learned, it's going to ask you for a certain amount of accuracy in most problems.